Today I would like to discuss another topic in my video series, which is the ratiometric design approach. The ratiometric design approach is essentially designing with ratios in mind. And the reason for that is because ratios are significantly tighter than an absolute value of something. If you had a resistor, you might have 10%, plus or minus 10% error on that, but relative to another resistor, it's going to be a lot tighter than that. And in fact, depending on how you size these resistors, it's possible to get a 10 to 100x improvement in this relative accuracy compared to the absolute accuracy of a single unit. And this goes beyond resistors. This applies to capacitors. It applies to FETs as well. So in the example that I have below, we have two different ways to generate a voltage. The first one on the left, we take a precision current and force that into a resistor, and that generates the VREF. Now, there's two error components that are associated with this. You have error on IREF, and then you have the absolute error on the resistance of the resistor. And on the right, we have a precision voltage, which has its own error as well. And then we've got a resistor divider to generate VREF. And here, the error that we are concerned with as far as the VREF voltage is basically the ratio between those two resistors, because that's really what matters. The absolute value is going to determine what the current flowing through that branch is, which may not be as critical if our primary goal is to generate the VREF. So now I'd like you to think about this and tell me which of the two you think would be a better approach if you're looking for a precision VREF. It would be the one on the right, and I'm about to show you why. So if we're still looking at the one on the left, we can assume that we have a trimmed band gap, or we have a trimmed current reference, and the accuracy that we can achieve is plus or minus 1%. However, the absolute error on that resistor is plus or minus 10%. So if we look at the error on the output, assuming that these two error sources are uncorrelated, then that results in effectively plus or minus 10.05% error in your output. It's effectively dominated by that resistor. Now, if we look at the other example, and we have the same accuracy on the band gap, plus or minus 1%, and the absolute error of the resistor is the same at plus or minus 10%, but now we have one additional error that we're looking at, which is the relative error. And the relative error, depends on how you size it, but in this example, I decided to keep it at plus or minus 1%. That means the top resistor is going to be plus or minus 1% within the bottom resistor. So now, because it's ratio based, the error is now the band gap and the relative error. So this works out to be plus or minus 1.4%. So it's significantly better than the other example. And the reason that you just have to look at relative error is because your output, your VREF, is equal to the R divided by R plus R times VBG, which works out to be R over 2R VBG. R's cancel, and you're left with 1/2 VBG. It does not depend on the absolute value whatsoever. It depends on the relative matching between those two resistors. As I mentioned earlier, MOSFETs can be relative as well, and so can capacitors. And with this in mind, the FETs that you use within your design should all be sized for some ratioed parameter. And of course, there are always going to be exceptions to this, but in general, what I have found to be most useful is to create a unit transistor and scale it up based on how much current is flowing through it. And that basically will result in a device with uniform current density. And that device is going to match very well. If you look at a current mirror, that's a great example of a ratio design. You have, if you have a current flowing through your diode branch, and then you have a 2x copy of that device hanging off the other side, it's going to draw twice as much current. And that ratio holds up pretty nicely. And the same can be extended to how you bias design. So if you're looking at your cascode structures, they should be ratioed off of these unit devices as well. And it's important to note that while you may have a design that works, if you don't follow this, it might not be very robust. And one important consideration with design is having high yield. If you don't have a high yielding design, then in my opinion, you don't have a good design. It's essential to have as high of a yield as possible. And this approach lends well to that. It makes your design very robust, very agnostic to the process that you're working in, because it doesn't depend on a particular parameter. What it depends on is how many physical devices are located in a given branch. And using this method, I have been able to port designs from one PDK to a completely different PDK, and you hit the simulation button on the first try and it works. Of course, there's always going to be some tweaking. You need to get things back in the region of operation you're looking to work, for your device to work, but still it works well, and just highlights how robust your design can be if you follow a ratiometric approach. And yeah, so a really good example of this is current mirrors, and I have one of those below, but the first example I want to show is biasing a cascode structure on a diff pair. So the example below is a differential pair that has cascoding on it. The cascoding is done by M3 and M4, and I want to highlight this example because I think it shows why ratios work so well. Now, a poor way to bias the structure would be if you were to take the gates of M3 and M4 and then bias it to some voltage potential V1. This voltage potential is just a voltage. It's going to stay pretty constant. It's going to be uncorrelated to certain parameters, such as the threshold of the devices there. So if that's changing with process, then or mismatch, then the bias point there is changing, and you're not going to be able to get as close to the limit, which in this case is the overdrive of M1 and M2. You're going to have to provide more room to allow for those variations. And in general, because there are more variations, it's going to make it not as robust. Now, if we were to delete that and then apply the proper bias, and there's many ways to do that, but the one that I'm showing here is basically biasing off the VTail node. So here we have VTail, and what I've done was I've branched off I branched off the currents here such that we have I flowing in the left branch, I1, and then we have I1 flowing in the right branch. And there's a current source on the bottom which essentially leaches a quarter I1 away from the top current mirror. And what's going on here is we're trying to bias this M5 device, and this M5 device is providing the bias for M3 and M4, and this is very similar to a wide swing in the sense that what we're trying to do here is we're trying to manipulate the current density of M5 such that the VGS is effectively a VGS of 3, 4 plus an overdrive. So if you break that up, what that means is we need a VT plus 2 VOV. And the reason for that is if we have 2 overdrives relative to the one on M3 and M4, that means we're an extra overdrive lower. So when we go back up, it provides that overdrive of room on M1 and M2 of the diff pair, ensuring that they stay in saturation. So to do that, as I mentioned, you need a quarter of the current density. And the reason for that is because if you look at the ideal square law, which is ID is equal to 1/2 K prime W over L VOV squared. If you rearrange for VOV, then what you get is 2ID over K prime W over L root, right? So in order to double the overdrive, you need to 4x something in the numerator or reduce something by 4x in the denominator. And the bias here is a quarter for M5. So what that means is we're starting at a lower current, and now we need to increase something by a factor of 16. So we have so we get back to where we need to be in terms of the bias potential. And what that means is if we have M5 set to be 1/16 the aspect ratio of M3 and M4, then what this works out to be is it would be 2 times 1/4 ID over K prime times 1/16 W over L square root, right? And that works out to be square root of 4, which is just simply 2. So there we would have 2 VOV relative to M3 and M4, which is how we get that overdrive impressed upon the drains of M1 and M2. And the other thing you could do would be to, instead of having a quarter eye, you could have just eye, and then you would have a smaller physical area. But the problem with that is now you're trading physical area for power dissipation. And that might be acceptable. It just depends on your application. But more often than not, it would be better to minimize the power through this branch, so you can dedicate it to the input pair. The last design that I would like to talk about today is the wide swing cascade structure, which I've drawn below. I think this is another great example of a ratiometric design approach. As I mentioned, current mirrors are a great example of that in general. Now, as far as cascading goes, it's entirely possible to not make the connection with this diode structure over here. We can actually break this connection and apply a voltage to some potential to induce VGS drop across the other two end-fed cascade structures. And in doing that, once again, we are sensitive to the parameters of those devices, because the voltage V1 over here is going to be more or less uncorrelated to any of the parametric variations upon those two devices. So with that in mind, what we want to do is generate the bias for that, essentially using the same device, because in principle that device is going to have the same or similar variations as the other devices in the cascade. And the way to do that is to put an NFET diode in the leftmost branch. And the way that this works is that typically it will be sized at 1/4 W over L, and the other 4 devices here are all considered to be double W over L. And as I drew above, the equation that we have is VOV is equal to square root of 2 ID K prime W over L. All right, pull that down here so we can start discussing that. So, just the same as above, if we have a quarter W over L, then what this works out to be is 2 ID over K prime 1/4 W over L root. And then from here you can pull out a 2 term. So that works out to be 2 VOV. So with that in mind, we are going up VGS here and back down a VGS here. But this is a VGS2 and a VGS1. They are not the same, right? So if we look at the one on the left, we just derived that's effectively going up a threshold plus 2 VOV, and then we go back down a VGS1, which is simply a threshold and a VOV. So this works out to be a VOV. So we have impressed upon this drain and this drain the overdrive voltage, the VOV and the VOV. And in doing so, those 2 devices are going to be well matched because they have a similar voltage across them. They're cascaded, so they have a high output impedance. They're going to be a very accurate current mirror. And perhaps one of the most important benefits is that because this node is an overdrive, we have significantly lowered the output voltage requirement at this node right here, because now we only require 2 overdrive voltages to stay in saturation, whereas in a simple cascade, that's not the case. To get back to the ratiometric design approach, the reason that this works so well is because those devices are all matched to one another, including the bias. If we didn't have that bias there, if we had something that was more like a low voltage resistor type bias structure where you had a structure that looks kind of like this, where you draw it real quick. Like this. This works as well. In fact, I've used it before when biasing might not be critical, but whenever I use it, I always make sure that I have extra room at the drains of the current mirror, because with variations in R here, it's possible that this drain and this drain might get squeezed into triode, and then you're not operating in a desirable place. So what that means is you've given up some of the output voltage requirement because you're trying to make your design more robust from that perspective. So it's a valid solution, but it's not as robust as something like what we've just discussed above. Additionally, having that resistor there is going to consume likely a lot more silicon area, and that's expensive. That's oftentimes we don't have much of that available. So wherever possible, you don't want to use these resistor components. It's better to bias with the FET, and it's more than one benefit in doing it in that manner.